Hi, so welcome back to this lecture. Here in this one we will learn about group homomorphisms and normal subgroups. Okay, so these are two very important concepts. The first is group homomorphisms, which actually connects one group to the other through a function, and that's what is called a homomorphism. So let's get to the definition of it. So suppose we have a function h, which is a function from one group to the other. The first group is called g with a binary operation dot. That's just the notation that we're using here. And the second group is called h, and the binary operation there is star, is what we denote this operation, this binary operation. And suppose this function follows a particular condition, that is, if it acts on a product of two elements from the first group, that is g, here a and b must be elements of g. So let's write it properly here. So here a and b, they will have to be elements of g. If I take two elements from the first group and I product them means with the binary operation dot, and h acts on it, then of course this entire thing is an element of h, because the function takes this whole element. This ab, by the way, is an element of g because dot is closed, because g is a group. Okay. So h acts on AB, which then becomes an element of h, and it must follow that this element should be equal to the product of the action of h on the individual elements. So h would act on A and h would act on B individually, and if you product, then these are now elements of h because h acts on A. These are images of A and B in h. And if you product them together in H now, because HA and HB are elements of capital H, so if you product them, that must be equal to the action of H on the product of AB. Okay, so if H, this function that we're defining from the first group to the second group, if it follows this condition, H of AB is equal to HA dot or star HB, okay, then H would be called a group homomorphism from G to H. Okay, so this is an important condition. For a function to become a group homomorphism, it should follow this kind of a condition. Exactly this condition. Okay. Now, of course, as an example, let's take Z, which is the set of all integers. Let's take the first group G to be Z with our normal addition, and the second group is also Z with our normal addition. So G and H are really the same in this example. Okay, so suppose I take the same group as both the domain group and the range group, and if I define a function h by, say, suppose any number here goes to 2 times that number. Okay, so for example, 5 as an integer would go to 10 as an integer. Okay, so the question is this a homomorphism? Well, this is a homomorphism, because what you do is, if you take two elements from the first group Z, okay, and you product them, by product here I mean add them. Okay, so that's a confusing statement, but if you think about it, the binary addition, the binary operation here is the addition. Okay, so when I say product, that's a loose word that I'm using, but really what I mean is the binary operation on A and B. Okay, if that's the new element which you get by operating this binary operation on this A and B. So if you take h of, so dot is replaced by plus here because the binary operation on this group is plus. Okay, addition. So h on A plus B, what's the definition of h on A? Whatever this element is, this becomes twice that element. Okay, so h acts on A plus B to make it twice that element. Okay, but we know how multiplications work. It's going to be 2A plus 2B. But 2A is the h of A. That's the definition. And 2B is the h of B. And that's again the definition. So what we have is And see, this plus is this plus here because this group also has the same binary operation, H, the second group. So this is a homomorphism, group homomorphism, because H takes an addition of two elements to the addition of the action of H on the individual elements. Okay, so that's a group homomorphism. Let's take another one. Suppose I take the group of all real numbers with addition as the first group, and I take the group of all real numbers except the 0 and multiplication as the second group. Okay, so here the two groups were the same in this example. In this example, let's take the first group as R with addition, and this one is R star, that is R without the 0, and this is multiplication. So they're all different. And if I take a homomorphism which takes any A to e to the power A, for example. Okay, the question is this a group homomorphism? Well, let's check. If I take H of A plus B, remember the binary operation here is plus. So if I take two elements A, B from R and I add them, then what's the definition of H? Whatever you take from the domain, the image becomes to that element. Okay, so this becomes e to A plus B, right? By definition of H. But we know what e to the A plus B is. That's just e to the A dot e to the B, right? By dot I mean product. Okay, multiplication. And that's H of A, because that's the definition of H. Product with H of B. And you see, this is a group homomorphism because you started out with two elements of this group R. You multiplied them. You added them. And then finally you got the multiplication, which is the second operation here, the operation in the second group. Multiplication of the action of H on the individual elements A and B. Okay, so therefore this is a group homomorphism as well. Okay, so these are just examples, okay, of group homomorphisms, and they're important to see how one group is connected to the other. Okay, now there are a couple of properties which are really easy to prove. One of the important properties is that it takes H, if H is a group homomorphism, H will take the identity element in G to the identity element in H. So I'm writing IG or 1G for the identity element in G and 1H for the identity element in H. So it's just going to be that the identity element will go to the identity element under a group homomorphism. Okay, so that's again very easy to prove. Let's just see quickly why that happens. So, for example, if I multiply the identity elements together, okay, what's that? That really, or you know, what you can do is, this really means it's multiplying the identity of G together. Okay, so 1 acts on 1 to give you 1. There's no problem with that. But we know, so I may miss the dot sometimes, but really what I mean is the dot is there. Okay, that's by abuse of notation, but the dot is always there because when I put two elements of G together, it means that there is a binary operation in between, and if dot is a binary operation, then dot must be in there. Okay, so now because H is a group homomorphism, of course you can break this up into the individual products. So star, right? So what you have, if you omit this part in the middle, this term in the middle, what you have on the two ends is H of 1G is H of 1G times H of 1G. Okay, so now these are all elements of capital H, if you see. Okay, these are all images of elements from G. So this is an element of H. So are these, because they're the same. But H is also a group. Okay, so these these elements, for example, h of 1g, this whole element, which is an element of this group H, will have an inverse. So if I multiply this equation by the inverse of this, if I multiply by the inverse of h of 1g, also on this side, if I multiply this by h of 1g inverse, then what you see is on the left you get 1 of h, because, so when I say multiply, I mean by this binary operation. Okay, so this gives me the product by star, product of an element and its inverse, so it should give me the identity in H. And from the right, well, I have associativity, so I can look at first this product. This is again the same thing, the product of an element with its inverse, with star as the binary operation, and that is again 1H, because that's an operation happening in H, so it gives me the identity of H. That starts with H of 1G, but identity on any element keeps it as it is, so you have H of 1G. So the identity of G under H goes to identity of H. Okay, that's just simple. Okay. Similarly, you can show this one. You can show the next important result. So let me just rub this out. That H of A inverse, so the action of H on the inverse of an element is to give you the inverse of the action on A. So if you have A, H on A inverse will be HA inverse. Okay, so this is first it takes A to H, and we call that HA. And to give you the H of A inverse, you just have to invert the element HA. Okay, so that's the meaning. In other words, you can take this inverse sign outside. Okay, let's just do that. If I take if I take H of A with A inverse, okay, again with a dot in there because A is an element of G. Of course, we know what this is. This is H of 1. By 1, I mean 1G, okay? Because these are elements of G, so when you product 1 with its inverse, it gives you the identity element in G, so that's 1. I'm writing 1 because of lack of space here, but it's 1 of G, okay? And this, of course, we have found that 1 of G will take you to 1 of H. Okay, now this is a homomorphism, so it will product it out. So this will be H of A, H of A. This first element with the second element, of course, there is a star in there. Okay, again, if I omit the sign here, it means star because these products, this is happening in H. Okay, so right, so we look at this equation. So H of A, which is an element of H, and H of A inverse, which is again an element of H, they product together with a star to give you the identity in H. But then this must be the inverse then. Okay, if you have an element and you get another element which multiplies it to give you the identity, then this must be the inverse of this element. Okay, that's just the definition of an inverse. Okay, you see, this is the element we are concerned with. We have to find the inverse of this element. That's what we're claiming. We have found some element here, H of A inverse, which is multiplying this thing to give you the identity. So therefore, H of A inverse this element will have to be the inverse of this element, which is H of A inverse. So and that's what we got here. Okay. So these are two very simple but important properties. These are true always. Okay. And you can check that in that example where we took R plus to R star with multiplication. In this one, where A went to e to the A, what's the identity? So let's check this one. What's the identity in the first group? It's 0, because we are here with addition, and the additive identity is 0. Okay, and h of 0 is, by the definition of h, is e to the 0, and that's 1. And 1 is the multiplicative identity for multiplication. So the identity in the first group goes to the under h, goes to the identity in the second group. Okay, and similarly for inverse, if I take h of some element inverse, by inverse I mean inverse in the first group, which is R, and so that would be minus A, because minus A is the additive inverse of A in this first group, which has addition as the binary operation. This, by definition of H, should go to e to the minus A, and then we know that this is the multiplicative inverse of e to the A, because e to the A multiplies e to the minus A by multiplication to give you 1, which is the identity. Okay, so e to the minus A is really the inverse of e to the A, and that's what it means. Okay, h of minus A is e to the minus A. That's the inverse of, if you take the individual action, that is e to the A, and then you invert it. Okay, so that's what it means. So it holds. Now, so with this setup, we move forward to something a little bit more interesting, and that is, because we have this homomorphism, or this function which follows a special condition, we are going to look at those special elements in G which are all taken to the element 1 in H. Okay, so here is the definition. So I'm looking at a set here. It's a subset of G because I'm taking elements from G. Forget the name, I'm coming to the name. But if I look at this set as a subset of G, this first group, I'm taking elements from G such that the action of H on those elements will take it to the identity in H. So what I mean by 1 is 1 of H, but even if I omit it, that's obvious. Okay, so I'm looking at those special elements which under the action of H are taken to the identity element in H. Okay, and I collect all of those elements together and I will give it this name, which is called the kernel of H. Kernel. Okay. Now, of course, one thing is sure, that 1G, that is the identity of G, that must belong to the kernel. Because we have seen that H takes Ig to IH. So Ig must be one of those A's which are taken to IH. Okay. So this is a non-null set. In other words, this set, the kernel of H, this is not a null set because the identity of G has to belong to this by its property. Okay, but there can be other elements. Okay, there can be other elements in G which are taken to the identity in the second group H. Okay, and those together is what is called the kernel, and what we're going to do now is, so the kernel will turn out to be very interesting because it will lead us to the next topic, which is the normal subgroup. Okay, so let's see what this special group has in store for us. Okay, what properties does it follow? So let's just rub these rough works out here. So come back to what we had. So this is the kernel. Now it has its own properties. It's two very interesting properties. Is that first of all, this is first of all, it's a subset of G, as we have by construction. It's a subset because we're taking elements from G. Now it will turn out to be a subgroup of G. Okay, that's a very interesting fact. Okay, if the kernel of any homomorphism will be the subgroup of the domain group. Okay, let's see how. So to show that this is a subgroup, we must go through all the 4 axioms. We'll do that very quickly. Okay, all the 4 axioms of being a group. First of all, does closure property hold for this set? Okay, this subset. Does closure property hold? For example, if I take two elements, A and B from this kernel, I'm going to call it K, just for a shorter version of this kernel H. If I take two elements from this K, the question is AB, the product of A and B, is this an element of K? That would be the closure property. Well, it will be an element of K if under the action of H that this element, this product goes to H, one of H. If it goes to the identity of H. So let's see. Does it go to the identity of H? Does this product go to the identity? By definition, then it would belong to the kernel. Okay, because it contains only those elements which under the action of H go to the identity of H. So this, because H, so let's see if this becomes 1H. H is a homomorphism. That's what we're dealing with. So this will break up A and B. Remember, again, there's a star sign in here, but I'm omitting it on purpose. The faster people get used to that, the better, because this operation is happening in H. So it's obvious that whatever operation is in here must be the operation that's assigned to H. Now, of course, these are elements of K, so under the action of H, they both become 1H. But that's identity on identity that gives you identity. Okay? So therefore, under the action of H, AB, this product is IH or 1H, the identity of H. So therefore, by definition, this must be an element of K. Okay? So therefore, the closure property holds. Associativity is, again, the easiest one because this is a subset of G. If we're using the same operation for K. To show that this is a subgroup, we are really using the same operation, okay, as G. Because this operation, this binary operation was associative in G, it has to be associative in K. So that's clear. What about the identity element? What's the identity element in this? Well, we know, as I said, this was an element of K because of this property. H took 1G to 1H, and therefore 1G must belong to K. Okay? But that's the identity. That's the identity in G, so it must be the identity in K as well. Okay? So the identity of G belongs to K, and because it's a universal identity on G and K happens to be a subset of it, so it must be the identity element of K as well. So therefore, this is the identity element in K. What about inverse? Inverse would be, so if I have an element A in K, the question is the inverse of that element also in K? That's the question, okay? Well, let's check. This will be in K if under the action of H, this is 1H. Okay, so let's see if this turns out to be 1H or not. Well, we have this nice property in here. That's HA, the whole thing to the -1, the whole thing inverted in H. But H on A is 1 because A is an element of K. So under the action of H, this must be 1. So you have 1H inverted. The inverse of the identity is the identity itself. So H on A inverse gives you 1H. So if A is an element of K, then A inverse must be an element of K by this condition. Okay, and so all the conditions of all the axioms of being a group holds for so all the axioms of being a group would hold for the kernel, and so therefore, because it's a subset, it would become a subgroup of G. Okay, so that's the first one. There's another important thing here, which is important property here, is that if you take any element of the group, any element G, this new subset, okay, which is actually called the conjugate, but doesn't matter what the name is, this will be a subset of K. Okay, let's see what this means. So first of all, what does this mean? G, K, G inverse. What does this mean? It means, what kind of a set is this? It means all elements, so it means elements of this kind, G, K, G inverse, where K is an element of the kernel. Okay, by K here I mean this kernel. Okay, so let's just write K here. Okay, that's a shorthand for kernel. So by this set I mean the collection of these elements. Okay, so individually you take all elements from K, capital K, and you form these new elements which are actually called conjugates. Okay, K is a conjugate. This whole thing is a conjugate of K by G. That's the name of it. Okay, so yeah, I mean, I'm not going to write it, but that's the name. This is the conjugate of this element K by the element G in the group. Okay, conjugate. Let's just write that down. This is the conjugate of the element, and this whole set together, this is called the conjugate of this whole thing together is the conjugate of K, and both of them will be by this element G. Okay, that's the name. So the conjugate of this kernel will be the collection of the conjugates of the individual elements of the kernel. That's what the meaning is. Okay, so for example, if K is a finite set, if K had just 3 elements, K1, K2, K3, then you would just have, so G, the conjugate of K, would just be G on the conjugate of K1 by G, the conjugate of K2 by G, and the conjugate of K3 by G. That's it. Okay, that's it. So that's what it means. Of course, this can be an infinite set as well. Okay, I've just listed this as 3 elements because I'm taking this to be finite, but this could be something else. And that means, even in that case, it would mean that you take each element from this capital K, you conjugate them by G, put them all together, then the whole set will be conjugate of the kernel K. Okay, the set. Okay, turns out that this is actually a subset. Okay, this is actually a subset of G, and we're not going to prove that. Probably this will go in the assignment. So the conjugate of the kernel, or any subgroup actually, will become a subgroup of G. Okay, but the interesting thing that we're going to look at here is that this will be a subset of G, a subset of K. Okay, how does that hold? Okay, so let's just do that. First of all, when would this be a subset of K? Is if every element of this belongs to an element of K. Okay, so let's take an element from the conjugate. So an element of a conjugate would look like this, something like this. Okay, an element from the conjugate would look like G, some small k from capital K. Let's take this element from the conjugate of capital K. Okay, here of course small k belongs to capital K. Okay, let's take an element. I have to show that this is a subset, I have to show that this element belongs to capital K. This is a general element from the conjugate. If I can show that general element belongs to capital K, then every element of this should belong to this, and so by that logic, this should become the subset of this. So we want to show that this is a subset of K. In other words, this element, we have to show that this element belongs to K. When would this element belong to K? Only when, under the action of H, it returns you the identity of H. Let's see if that happens. Under the action of H, what does this do? This element G, K, G inverse, well, this is a homomorphism, so let's just break everything up. So you have H on G, H on K, H on G inverse, but that's the inverse of H on G by this property. And remember, I'm omitting the binary operations here, but all of this is happening in H, so there are stars in there, okay? And here there are dots, okay? But let's just omit all of that because I hope we're all used to this now. Of course, small k is an element of capital K, so that's the element of the kernel. So under the action of H, this should return you the identity in H. So this is 1 of H. An identity on any of these elements has no effect. It keeps them as they are. So this is going to be H on G with H on G inverse. And these are just the inverses of each other. And so it's just going to be the identity of in H. Okay. So therefore, this element from the conjugate of K under the action of H gives you the identity in H. So that must be therefore an element of K. So therefore, this should be, this element here, this should be an element of K. And since it's a general element, every element of the conjugate should be an element of K, and so therefore this conjugate is a subset of K. That's a proof. It's a nice exercise as well. Okay. Now turns out something more happens, that even K. Okay, and by the way, I think we should stress this more. This is true for every element G in K. In other words, so conjugate of K by every element in G must be a subset of K. Okay, because we did not choose G to be any particular G. G was some element, just a general element from capital G, the group, and the result was true. So what this means is that the conjugate of K will be a subgroup of K conjugate by any element of G will be a subgroup of K. Okay, all right. And I say subgroup because, as I said, this will become a subgroup of G, and as a subset of K, then this becomes a subgroup of K. Anyway, that's another statement. So let's come to another one. Something more happens, that also K will be a subset of its conjugate by any element in G. That's also true. Why would that be true? Okay. Well, to show this, we now have proven this, so we will make use of this one here. Okay. Let's just show this. So what we can do is, to show that this is an element, so this is a subset of its conjugate by any element of G. First, we take any general element G from capital G and we look at its conjugate. This is going to be its conjugate of K by G. I want to show that K is an element of this conjugate. K is a subset. So I will pick a general element from capital K, and I will show that this element from capital K belongs to the conjugate. That way, every element of capital K must belong to the conjugate. So K must become a subset of the conjugate. Okay, right. So let's just show that. So what I have here is to show that this happens. I will write this K in a slightly general form, in a slightly manipulated form. I have picked this G. Okay, this is a fixed G for this statement now. Now I will write this as G inverse K G inverse. I hope that makes sense, that this will finally turn out to be K. Okay, because G on G inverse will give you identity. This is happening in G, by the way. So all the products means the dots are in there. So G on G inverse will give you the identity in G, and G on G inverse again will give you identity in G. And so identity has no effect on K, so it will return you the K. So now, of course, by associativity, I can just bracket out a particular group in here. Now, what about this? The question is, this was true. Okay? So G is a particular element here. So this is true that any conjugate of K is a subset of K. Okay? If G is an element of G, then G inverse is also an element of G. Of course, that's a group. G is a group. Let's look at the conjugate of K by this element, G inverse. The conjugate of K by G inverse is going to be the conjugate by G inverse is going to be, instead of G, you write G inverse K, and then this element inverse. So G inverse is just G. This is just inverse of the inverse. Okay, I hope that's clear. So conjugate by G means G, K, G inverse. Conjugate by G inverse would mean G inverse, K, G inverse, inverse. But G inverse is just G. So this is this. This must be a subset of K, because we have shown that any conjugate of K is a subset of K. This is any conjugate. It's a conjugate by G inverse, so it's a conjugate of K. It must be a subset of K. Well, now look at this element in here, the one in the bracket. This is an element of this conjugate, because small k is an element of capital K. So this element, because it's an element of this, which is a subset of this must be an element of K. So let me give it a name. Let me call it K1. So this whole thing is an element of K, which I'm calling K1, and G inverse. Well, what is this an element of? This is an element of G, capital K, G inverse, because K1, which was this element turned out to be K1. This element is an element of capital K and conjugated by G, so that must be an element of the conjugate of K by G. So therefore, K, which is an element of capital K, after this little thing here, turns out to be an element of the conjugate. And that's what we had to show. We picked an element from K. We wanted to show that small k would be an element of the conjugate. And that's what we have shown. Okay? Right. So therefore, by that logic, capital K must be a subset of its conjugate, and conjugate by any element, because we've picked a very general G from the group. Okay? So combining these two together, because each one is a subset of the other, we can combine them together and say that G, the conjugate of this group, okay, the conjugate of K by any element in G must be equal to K itself. Okay, that's a very, very special thing that's happening here. A subgroup, which will be a subgroup here, as we have shown, subgroup becomes equal to its own conjugate. Okay, and that's true for the kernel. Okay, so the kernel is a very special group which follows this very important condition, which is actually the condition of being a normal subgroup, and that's what leads us to the definition, and that's the part that we will continue with in our next lecture. We will just finish with what's the definition of a normal subgroup. So this is inspired by this particular equation here. We say that if there is a subgroup of G which follows this condition, just like the kernel does. Kernel was a subgroup of G and it followed this condition. So if N is a subgroup of G which follows this condition for all G, in other words, it is equal to its own conjugate by any G, any element G from the group, then N would be called a normal subgroup. So N, a subgroup of G, is normal if N is equal to its own conjugate for all G in the group. Okay, this is the definition of a normal. So therefore, the kernel for any homomorphism is always a normal subgroup, and it's written like this. So in notation, this is the subgroup notation. I think this is how we will denote it. For it's a subgroup, but with the triangle we mean it has a special character of being a normal subgroup of G. Okay, so a K for any homomorphism, any group homomorphism, because H was any general homomorphism, there was nothing particular about it. Kernel followed this condition, and so it's a normal subgroup. So the kernel, so let's just write that down. Kernel of any homomorphism is always a subgroup of, it can be equal, I mean, it's always a subgroup of the domain group. Okay, always. And inspired by this, that's how we define what a normal subgroup is. Okay, all right. So we will finish this here, and we will say more about normal subgroups in the next lecture. Okay, thank you.